Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video demonstrates how to use frequency distributions. Let's get started. Well, first we can use frequency distributions to better understand our data. Perhaps the quickest and most powerful message a frequency distribution communicates about a data set is its shape. To see the shape of a frequency distribution, just imagine that there's a line connecting the top of each of the bars in your frequency distribution. So if you do that for the frequency distribution you see here, the shape would look something like this. And this shape is very special because it roughly approximates a normal distribution. Now, we'll be talking about normal distributions much more in depth later in the course. Okay? For now, all you need to know is that the normal distribution has a very characteristic bell shape, meaning it looks like the outline of the shadow a bell would make. The frequencies start low, so here on the left they start low, then they come high around the center, and then they come back down in a symmetrical fashion. Now, symmetrical means that if you drew a line down the center, each half would look like the mirror image of the other half. Now, when you're judging subjectively whether or not a distribution shape is normal, don't get caught up in little deviations and other such details. Just look for the general trend or an approximate likeness to this shape. For example, the shape you see here with this frequency distribution is not exactly symmetrical, yet this distribution would be subjectively judged as approximately normal. Now, frequency distributions sometimes have gaps. Gaps are important to note because they can indicate the presence of more than one population in your data set. Now, the reverse is not necessarily true. A gap often indicates the presence of more than one population, but just because you have more than one population does not mean that you're going to have a gap. It depends on how many classes or categories or bins you use to create your frequency distribution. If you have too few, it can hide the gaps that would indicate the presence of more than one population. Let's look now at an example. Here's a frequency distribution for a data set of the weights of US pennies. We got a sample of pennies here and we weighed them all. We found that 18 of them have between 2.4 and 2.49 grams. 19 of them are between 2.5 and 2.59 grams and so forth. Now, notice the presence of a gap where there's no data being reported. Okay? This set of zeros here is indicating a gap. There's no data in any of these bins. This means that we actually have two populations of pennies. One over here in the lighter weighted region and one over here in the higher weighted region. Now, sometimes gaps exist where very little data is reported for a category. That means you don't necessarily need to look for a 0 to identify a gap. Sometimes it could be just a 1 or a 2 or some low number like that. It just depends on how many data points you have, how many categories you have, and what the frequency counts in those categories are. But generally speaking, you're going to be looking for zeros to indicate your gap. Now, in this example here, you've got two different populations because there was a change made in how the U.S. Mint manufactured pennies. This change occurred in 1983. So if your penny was manufactured before 1983, then your penny was composed of 95% copper and 5% zinc. But after 1983, pennies began to be made with 2.5% copper and 97.5% zinc. Zinc, being a less dense metal than copper, is much lighter than copper, and so the pennies that we see up top these are the ones that are weighing less. Okay, they were made after 1983. The pennies down at the bottom of the frequency distribution were made before 1983. Now, you might be wondering, what's the big deal with 1983? Why did the U.S. Mint make the change? Well, there's quite a bit of a deal, as it turns out. 2 years prior, in 1981, there was a coup in the country of Chile. Chile is one of the world's major producers of copper. Well, there was this coup that took place in the country. The military took control. They didn't take too kindly to the United States because, quite frankly, we interfered often in their affairs. As a matter of fact, the U.S. government actually sponsored some of what happened, clandestinely, of course. Thank you, CIA! After the coup, a guy named Pinochet gained power and was basically torturing his own citizens. Human rights violations galore. Yeah, he came to power in part because of things that we did to help set it up. So, yeah, thank you, CIA. It's an interesting story to look into if you don't know anything about it. But long story short, we had to make some choices when our supply of copper got reduced. Pennies didn't win. Frequency distributions often allow for in-depth analysis. Let's look at this example here. This frequency distribution is showing the heights of a sample of people at Vassar Road Elementary School. So you got definitely one population here and another population down here, okay? Because here in the middle, you've got this gap. So what would actually explain the two populations here? What do you think? Well, think for a moment about what the data represent. Okay, the data represent people at an elementary school. So you've got one population up here that's really short, and those are the kids, and then you've got another population down here that's much taller. These are the adults, the faculty, and the staff. So identifying gaps, as well as the shape of your distribution, can actually reveal characteristics of the underlying data. So if you go and make frequency distributions from the data we saw earlier for Best Actress and Best Actor Oscar winners, you get what you see here. So Best Actress is on the left, Best Actor is on the right. Now, if you want to see if you can make these on your own, feel free to pause the video and then go into StatCrunch and make these frequency distributions on your own. Okay, with these two distributions side by side, what can you conclude from comparing them? Well, one thing you can do is observe the shape of your distributions. Where is the bulk of the data located in each? For the Best Actress distribution, the data seems centered or towards the left. Okay, but for the Male Actor distribution, the data seem less shifted and more centered. Now, look at the categories those centers correspond to. Okay, it seems that when it comes to movie stars, we like our women a little younger, and we like the men to be a little older. You can also observe the tails of the distribution. The tails are where we have relatively less data. Notice the age ranges for the tails that are on the right. It seems we have higher tolerance for older men in movies than we do for older women. Now look at the tails on the left. There's not much of a tail there for the ladies, showing a clear preference for seeing 20-something ladies than 20-something gentlemen. Do you see how observing the shape of the distribution and where the data are amassed within a distribution can reveal information about the underlying data? Well, these skills are like any other. They get better the more you practice them. So don't get discouraged if you can't see right away everything there to be seen. Just keep practicing and you can improve. Practice makes perfect. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching, and I'll see you in the next video.